Good evening, everyone. Welcome to IA discussions. So today is our second video. Yesterday we have seen first video on what kind of IA can be done. How do we start building our IA? How do we start building our RQ? Then define our hypothesis. Then define our variables and so on. So we'll conduct a similar session even today also. Okay, but with a different experimentation. Okay, now let me just share my screen to show you what is that we are going to do. Just a moment. So, as you are observing, the second problem today is something like this. How does the variable affect the horizontal distance in projectile motion? Most of the time, if you observe, we ask any batch of students, okay, definitely there'll be one pendulum experiment. Okay. So there'll be variations of it. Maybe 2 years before what people have done, the same thing would have been done this year. Something would have been changed. Okay. So here also we'll look at what kind of experiments can we do. How can we modify something and we can view something as completely new. Okay. So the simplest RQ that one can do with this is that they can ask a question, how does a variable, so we do not know what is a variable, like yesterday what we have done, affect the horizontal distance, okay, in a projectile motion. That's what we're going to do. So towards it, what we are going to do is we are going to look at the horizontal projectile motion. So what is that I have done now? I have done something like funnelizing. What do you mean by funnelizing? Which means that initially you had a broad problem, named as projectile motion. Then suddenly I narrowed down and I said, I'm not looking at the oblique projectile motion, but I'm looking at the horizontal projectile motion. So partly 50% of my problem is now defined. Okay, so this is where we need to look into. Now the broad question is, we started with motion. Maybe we can look at energy, we can look at the heat produced. So anything can be started with this. And then this can be written into the narrow focus, could be projectile motion. And examples of projectile motion, why are we interested into it? Okay, something like you can say about basketball throw. You can say about the food packets being dropped from a helicopter in a refugee camp, right? Okay, so that is what one more example of a projectile. So from there, I came to an conclusion that I thought, okay, why don't we go on for looking at a projectile motion which is horizontal in nature. Okay, we call this a horizontal projectile motion. So which means that you have something like this. Let me just write it down, show you what kind of motion I am talking about. Use my pen over here. Right. So usually the projectile motion that we talk is something like this. This is the projectile motion we talk. But the current projectile motion that I'm talking is, you're standing on a cliff and you are throwing it from here, and this goes like this over here. Right? We're looking at this projectile motion, horizontal projectile motion. And again, when you talk about this horizontal projectile motion, there are several constraints over here. The first one is you can vary the height. Okay, you can change the initial velocity. You can see several things over here. So what did I do? Okay, you can save this particular slides if you want. You can take the snapshot of this and you can carry out your question based on the same way. Okay, next, what did I do? The next thing is that now once when I have this, I want to know what is my variable. Okay, because I already know what is my dependent variable here. This is my dependent variable and this should be my independent variable, which I do not know. What variable should I change? So one of the example is mass of the object. I can take a ball from here and throw it across. Okay, the ball could be a tennis ball, the ball could be a volleyball, the ball could be a football, or maybe I can take an iron ball. Okay, if I'm strong enough, right? So therefore it could be a ball. So the mass of this object will definitely change. Now, if the mass of the object change, does it change the path? Does it change the horizontal distance from here? That could be one idea. The second idea could be something like the vertical height. Okay, if I am standing from here, if I am now throwing from here from a height of, let us say, 1 meter. Okay, I am throwing from here. Okay, what is the distance which it falls? If I now lift my hand and throw it from a much larger distance, what could be my distance? Right, I can ask that question also. So this question is valid. This question is also valid. Right, you can do an experiment based on this. Then initial velocity. I can change my initial velocity. I can take a bat and hit it. Right, I can change the initial velocity over here. Okay, and as a result of it, some balls, if I make it move faster, then it might land at a larger region. Okay, let me change my ink once again here. Okay, let us say, if I hit it from here at a larger velocity, it might land here. If I hit it with a much smaller velocity, it might land here itself, right? So therefore, definitely it depends upon the initial velocity. Okay, so this is also possible. This is also possible. Then time of fall. Okay, So is it that, okay, when larger time, does it fall at a much larger distance, or shorter time, does it fall at a lesser distance? You can do it, but how do you exactly time? Okay, this is a bit questionable over here. Okay, so because when you talk about an independent variable will always be something like it should be varied in equal intervals. Equal intervals. Okay, let me change my pen. It's not clear. It should be defined at equal intervals. For example, when you take the mass of the object, I can take masses of the object to be something like, I can take initially a 5-gram object, 10-gram object, a 15-gram object. See the intervals here are 5 grams each. I can always choose this. Nothing wrong. Vertical height, for example, I have initially chosen this height to be around 1 meter, 1 meter, 1 meter initially. Then I could choose this 1.2 meter, then 1.4 meter. I can keep a stand, right? And I can keep on pushing the object from there. So this is also possible. Then initial velocity. Now this is a problem over here. When it comes to initial velocity, I should throw this at a speed of, let us say, for example, 1 meter per second. Okay, 2 meter per second, 3 meter per second. But how do you throw it? Okay, it's left to you. Okay, if it is feasible, then you can proceed with this. So this is once again a questionable one. Time of fall. Okay, so time of fall is a headache. Okay, how do you choose the time of fall? Can you say, okay, the time taken by the object to start there and to reach the bottom, it should be something like 1 second, 2 seconds, and so on? No, gravity defines the time. So therefore, you cannot do anything over here. You cannot exactly pinpoint it. So this, I feel, is not a feasible one. So I will not consider this. And this also, okay, is not such an easy task. I'll come back to it as why it is not an easy task, and then we will see further. Okay, let me go on to the next few ideas. Air resistance. Now, how do you implement air resistance? It's a question over here. Okay, there are methods to implement air resistance. What you can do is you can make the air to be blown through a fan. Okay, you can put a fan on one side over here and you can blow the air, and as a result of it, the air can be uniform. But the problem there is that the air resistance should be uniform, right? If the air, say for example, I put a fan here, put a fan here, okay, and the air is blowing like this over here. Now, as the particle starts coming here, okay, it will experience less air resistance. When it comes here, it experiences more air resistance. When it is here, still more. And when it comes away from here, air resistance is zero. So it will not experience any air resistance, which means that you should keep a bigger fan completely so that the air is blown throughout the region as long as it falls down. Is it possible? So therefore, based on that aspect, I can say that maybe air resistance is not a feasible one. So therefore, I will still consider this to be a not possibility. Friction between the ball and the ground. This friction. What do you mean by friction? Friction means it's only about your coefficient of friction, which is mu. So how do you change? You can say initially I'll put a grass, then I will put a carpet, then I'll put a metal, then I'll put a wood, and so on. But are these measurable ones? These are not measurable ones. So therefore, do not use friction also. Okay, so friction, when I talk about friction, it should be a measurable one. Any independent variable, okay, should have 2 or 3 characteristics. The first one is it should be measurable one. Measurable one. Your IV should be a measurable one. The second characteristic is it should be changeable, or it should increment equal increments. It should be in equal increments. And the third rule, which I actually consider, is it should have some unit. Okay, don't consider something which is a non-unit one. Okay, so it's always better to consider something which is a unit, because when you draw a graph, okay, and we are going to interpret this in the evaluation, the unit will really be helpful for us. But there are conditions where, okay, there are conditions where I have taken unit less also. Okay, when we come back to that kind of experiments, I'll let you know, then you can look for it. Okay, but I need to justify it. Why did I choose unitless? And is it possible for me to choose unitless with unit? So all this I need to justify. I'll let you know at that point. Then, is a ball rolling, sliding, or jumping? See, what I can do is I can take the ball here. Okay, I can initially make it roll like this and make it fall. So might be it will change. Or maybe I will be able to bump it like this. I'll bump it like this and then make it fall over here. So therefore, it undergoes a path like this and falls over here. Sorry, this will not be seen. So this will be seen, and after that, this will fall like this over here. Okay, the time taken, or maybe the distance which it moves across might be different. But the problem is that how do you measure something over here? So is it that you are measuring bumps? Okay, when you say bounces are there, jumping for example, okay, how many jumps, how many bounces were possible? Okay, then one of the bounds could be larger, one of the bounds could be smaller, one of the bounds could be here only and it will fall here only, it will keep on falling like this only, it will fall over here, right? So this is also not a feasible idea to go with it. Okay, or maybe you might get chaotic results. So it is better to you not to choose things which are chaotic in nature. Okay, so therefore, now what we have done is we have already narrowed down this 3, 4, and 5. So 4, 5, and 6 we are not going to use. Then 3, 4 also I am not going to use here. I am going to use mass of the object, vertical height, and initial velocity. Okay, mass of the object, vertical height. I'll write here. Mass of the object, vertical height, velocity. Any of these three will definitely be useful. Now to use this, okay, the next question we need to ask is, what is the kind of instrument do I have, right? Because these are all something like feasibility problems. Okay, you need to look at that. So therefore, mass you can easily measure. So therefore, this is acceptable. Height you can measure it. Okay, from this point of view, edge is also acceptable. And velocity. When we come to velocity, I just was looking into it. I found out the velocity meters are available, namely odometers. Okay, but the cost of these velocity meters is very, very high, which is around 17,478. Who will buy this one? Okay, so or maybe if you have a Vernier or Lager Pro or so on, then there could be a sensor where you can use it, but you have to use it very carefully. Okay, so still a complicated one. That's why I told you, okay, I did not prefer this one. But on the other hand, if at all, if I am doing some technological innovation, let us say, for example, I am using an Arduino and then I am going to put something like an IR sensor and going to find out the velocity using a digital kit, then this is always a possible thing. There's one more way where you can find out velocity. Okay, let us say, for example, you can put something like video tracker software. Yesterday also in the video we have seen this. So there what you do is you track the motion of the object and then you find out, okay, what is the velocity at each instant or maybe at the point where it left. You can do it. So that's also a wonderful thing. Okay, you can do this. Okay, and yeah, so these are some of the examples where velocity can be determined. Okay, so of course you can use velocity. Okay, but if you are really tech savvy person and you are able to do it, then definitely go for velocity one. Okay, but you'll get lots of information using velocity vectors. You can find out how does the velocity changes. Evaluation part you can write many things. Okay, but now these two appear to be very, very simple. Mass. Okay, now we know from Galileo's experiment, when the mass is changed, gravity doesn't look at the mass at all. It attracts it with the same gravitational force. And as a result of this, the acceleration would be independent of the mass. Acceleration would be the same. I'm sorry, I mentioned gravitational force. The gravitational force will be different, but the acceleration would be the same. So therefore, the time of reach would be the same and the distance, okay, will not vary. Okay, now we'll see that later on. How does the distance depend upon the time of reach, which comes in the math part. Okay, so therefore, I would always try to go with the initial velocity. Okay, so initial velocity, these are very simple to work with. Mass, okay, it's a very trivial task. I will not go for it. Okay, meter scale. What is this now? Height, vertical height. Vertical height, I will definitely go for it. Okay, I can change the vertical height. Okay, and I can find out as the vertical height changes, how does the distance actually change. This is a feasible one. You can always do it. Okay, so you can go with this. And the other thing, just now when I was thinking about the other thing that you can do is that, okay, you can do something like this also. Let me change my pen. Yes, okay. Say for example, you kept the cliff here. You kept the marble or maybe any other object over here, and you kept on increasing the height. Okay, and this was the place where it fell actually here. This is the place where it fell over here. Now what you can do is, let us say this height, this distance can be fixed. Let us say 1 meter. Okay, and now what you can do is you can move this one backward. Let us say by 1.5 meter. This is maybe 0.5 meter over here. So when I do this, okay, see, it will not immediately fall over here. So maybe if I use a marble and a catapult, what can happen is that, okay, so this can go like this and it may hit the wall here. Okay, it can hit the wall and I can find out, okay, what is the displacement between these 2 points. Okay, so when I move farther away, it bends a larger value. When I'm nearby to the screen, it bends a shorter value. So therefore, now what I can do is I can also think about this distance could be your independent variable, and this distance could be your dependent variable. This also I can do, but okay, there are several problems associated with this. In fact, one of my student did this, okay, and she got 24 out of 24 okay, using this. But of course, there are several problems, and you need to know mathematically what is feasible, what is not feasible, and then work with this. Okay, now therefore, now we have only two possibilities. One is the height. Okay, height of this one can be varied, which means you have, this is your h1 height, then you can vary this height h2 here, then vary this height h3 here, h4 here. For each and every increase in the height, this will be your independent variable. Okay, if I drop from here, it will fall here. If I throw from here, then it will fall, it might fall here. If I do it from here, it might fall here, right? So your dependent variable could be the distance r. This is one of the variables. The second variable, in all these cases, I see to it that the velocity is constant. Velocity is constant. The second one that we have is that I can change the distance over here. I can do all these things. But then now the question here is that how do you ensure that the same speed is given to the object? Okay, this is a very difficult task to understand, right? Not so easy. Okay, I don't have any, say, I can have a sensor to measure things, but how do I make sure that I am hitting this with the same speed? So towards it, what you can do is you can do an activity like this. Where is it? Oh, I'm sorry, I missed it somewhere. Okay, fine. Anyway, I didn't put that. So what you can do is you can put an inclined plane like this. You can put an inclined plane like this, and this is the cliff. This is the cliff over here. Take a marble here, roll it from here. Okay, because you are going to change this one here. So when you roll it across, what will happen? Now let us say you put the actual object over here. You put the actual object over here. This comes and hits here. When it comes and hits here, it comes and hits with the same force. What is the force it hits? It hits with it moves with an acceleration g sine theta. And when it hits here, the force which it hits here would be mg sine theta. And if it is mg sine theta, and immediately when it hits, collision happens, and this starts falling, and it falls over here, right? So this is what happens. Now what I can do is I can now increase this height. Next one, I can increase the height like this over here, and then once again this will also go upwards. So the incline will look like this. Incline will look like this. Take the marble once again. The same mg sine theta is given, which means what? The same force is given, same velocity it gets it across, right? And as a result of this, okay, same velocity is given over here. You are ensuring that the velocity is same. You can do it like this. There's one more way of doing things also. So how do I do? I can use something like a spring. I can use like a spring over here, okay, and I can tie the marble over here, or the object over here, compress it to this much length, okay, and release it every time I do it, okay, as I lift the object. So definitely it will now release it at the same velocity. That's also possible. Okay, two methods I can do. Okay, so these are some of the important things that you need to look at. Projectile motion appears to be very simple, but it's not so. Okay, there are a lot of math being involved, a lot of creativity that you can do. So you need to look into all this, right? So therefore, the hypothesis that I can say is that if the launch height increases, then the horizontal distance will also increase. Okay, maybe it works, it doesn't work, that you need to look into it. Okay, I have just put across a hypothesis. So then you need to prove it across. Why it works, why doesn't it work? So how do you do it? You need to get the math behind it. Now we need to identify the variables. What is the variable over here? Independent variable is not a launch angle. This is nothing but height. Height. Dependent variable is your horizontal distance. Controlled variable is initial speed, which you're controlling by an incline, and the height, okay, is nothing but your. So here instead of height, I can say angle, horizontal motion. Okay. And then friction, air resistance. You can mention all this, and you need to mention about if these are not kept constant, then what can happen. You can mention that also. Okay. Next, relevant math concepts. What are the math concepts? You already learned projectile motion, horizontal projectile motion in your first year in your IB1. So when you have an object which is being rolled from here, it falls over here. So you first find out what is the time taken, okay, and then you find out what is the range over here. The concepts are simple. You write t is equal to square root of 2h by g and r is equal to ux into t, right? So this, making use of this, you can easily find out. Now as you see here, when r is now proportional to h, right, because when I substitute this here, I get as ux into square root of 2h by g. If ux is constant, g is constant, then t should be proportional to h, right? So therefore, when now when t is proportional to h over here, sorry, r is proportional to h, r is proportional to h. That means when you raise the height, the range will also be larger. Okay, and then you need to look at the graphs, plot a graph of dependent, independent variables, xt graph, vt graph. Okay, so all this you need to look at, and how do the formulas connect to your variables? You need to establish this relationship. Okay, once you get the math, okay, then definitely rest of the part becomes more easier for you. So math is very, very essential while you do an IA. Okay, because it will be useful not at the initial part, because IA doesn't say that you need to get a math. Okay, but if you have a math, then it will be very useful for you in your comparison studies, in your evaluation, everywhere the marks will get added up. Okay, now next, apparatus and setup. That's what I told you already here. Okay, so you have something like this. You have a table, you have a pile of books which has been added. You put the marble over here, and then you see this comes and hits here. Okay, and as a result of it, the marble falls over here. Okay, this is one way. The other way is using a spring. You can do this. So what are all the apparatus you need? You have got this one here. Okay, now, so you don't have doing this experiment from the feasibility point of view and also from the variable point of view, from your measurement point of view. All this has been cleared now. Now let us move on to the next one. Now we need to do the experiment. Now when we do conduct the experiment, so what is that we get? We get something like this. What do we have here? We see data collection. So what is the data collection? Launch height is changed, and then at the same time the horizontal distance also changed. So what happens? Okay, we have to look into it. And then once you get this value, what is that you need to write? You need to look at this table. See, any infographic, okay, is nothing but it gives you some information. Every infographic that you write, you need to mention what is that you understand from that infographic. Okay, so for example, here if you observe, when there are two things that you can write over here. First is you will have your data table will have something like uncertainties, and on the headers, and then you will also have number of trials. How many trials will you do? At most around 3 to 5 trials. If you do 5 trials, for example, okay, now these 5 trials, when you do 5 trials over here, you can get several values. Let us say, for example, first one you get 30, second one you get 30.5, third one you get 38, fourth one you get 31, fifth one you get 32. Okay, out of which, what is the first thing that you can do? You have to remove the outlier, right? You have to remove the outlier. That you have to say that the outlier was removed, and as a result of it, we found that consistently the distance was seen to be around 31. Okay, so we have got it consistently, right? And the second thing that we have seen is that what is the random error here? The randomness is already seen there. Okay, so we can mention all this over here. Next, once we have collected data, and then what is it we do? So this is for example, let us say is at height of 1 meter. Okay, so this is the distance range that you have measured in centimeter, let us say. If I make 1.5 meter over here, the distance where it falls could be 42, 41, 40.5, 40.8, 40.1. Now what did you observe? Just a minute. Yeah, what did you observe here? When the height increases, the range is also increasing, which means clearly that range should be proportional to height. Okay, but is it proportional to height? It's proportional to height, but not linearly or whatever it is. So later on comes your, okay, so linearizing all these things, and then you are going to plot a graph. All this comes over here. But preliminary thing is that when you look at a data collection table, what you understand from the data collection, that has to be mentioned. Okay, without mentioning that, you won't get marks, right? Okay, and then next is evaluation. So we have done criterion A, we have done criterion B, criterion C comes you in evaluation. So you need to look at what are the sources of uncertainty and error. Okay, why do you get lots of uncertainty? What was the error? Maybe the error could be because of the friction between the object and the floor. Maybe the floor is not clear, it's not even. maybe because of when you started the experiment. Okay, so you need to look at, okay, the timer. Okay, so how did you count the time properly? So many things that you do according to an experiment you need to mention over here. Limitations of your method. What are the limitations? Limitations could be, say, when you dropped, okay, say for example, you did it for a height of 1 meter, 1.5 meter, 2 meters, 2.5, 3, 3.5. How many? 1, 2, 3, 4, 5, 6. 6 observations I made. Okay, for until 3.5 meters I have done. Okay, and I observe that for distances of 1 meter and 1.5 meter, or maybe between any two consecutive trials, I'm not getting much of difference. Okay, I'm getting almost the same one. You can mention this. See, maybe if I had done this with experiments of 1 meter, 2 meters, until 7 meters, larger number of observations at larger heights, I would have got it properly, but unfortunately, you're not able to do it. That could be one of your limitations. The other limitation could be maybe the floor that I was practicing on, the platform in which the ball or the marble fell onto it. Okay, it was not uniform. You can put across the friction, you cannot make it completely zero, right? And what can happen is, let us say, for example, if this is my incline, this is my table, and you kept the object over here. Okay, so this marble came here, it fell here. The moment it fell over here, it would have bounced a little bit and hit it at this point. So as a result of it, it's a two-dimensional collision, right? See how depth we are going into. So as a result of it, okay, so this could have bounced like this and then fallen over here. So all this you can mention over here. Then suggestions for improvement. What is that you want to suggest? Okay, how do you improve this particular experiment? So look into that. And strength of your conclusion. Though you had so many problems, but still you observe that this R, if it is proportional to root H, then definitely you've done a wonderful job. And you can say, okay, with a simple experiment, I was able to do something like this. Okay, and maybe by plotting a graph of R versus H, you would be able to find, okay, see what is it? What is the expression for this? R is equal to ux into square root of 2h divided by g, right? The value of ux is known and the value of h and r are being estimated or determined using your experimentation, and the value of g is calculated using the slope, because you know this would be, how does it look like? It looks like ux by root 2 into root h, right? If I plot a graph of r versus root h, r versus root h, what do you look like? This is the y, this is your x over here, and this would be your mx. This would pass like this over here. You can find the slope. From the slope, if you already know this value of ux, you can estimate the value of g. If you get the value of g and your value of g consistently in all the observations comes out to be around 9.8, then you know you've really done a wonderful experiment, right? Because consistently you're getting the same value. So therefore, you can say this is the strength of my conclusion. Okay, and then as a bonus you are getting this. See, your interest was not to find out the value of g. Okay, your interest was only to relate these two. But okay, in addition to it, you are able to determine this also. Okay, and then next, finally, conclusion. Like in yesterday's video, we've seen this. So you should have a clear and direct answer to the RQ. Okay, so whether it satisfies your RQ that you have defined, or is it going against the RQ? Even if it is going against the RQ, okay, doesn't matter. Mention what is the reason, justify it properly. Interpretation of the processed data. Okay, so use the calculated range, or you can also use your simulated data. Okay, there are several simulations that are available. In fact, I myself yesterday I had done one simulation. Shortly it will be uploaded on the website. You can look into that also. Okay, and reference to associated uncertainties. You can look at the uncertainty in ux, uncertainty in the value of g, or maybe h or r, and then go for the propagated uncertainties, and finally get an answer for this also. Link to the scientific theory, which is nothing but the math. Okay, then now what you can do is you can compare the value of r that you get according to the math or prediction and according to what you have got it from the theoretical part, the experimental part. And then you can make a comparison of these two. You can say r experimental, r theoretical, and then find out what is the difference between these two. If your difference is much larger, mention why it is larger. If your difference is smaller, then you can say it is a bonus for me and I got it appropriately and I got it correctly. Source the citation that is traceable. Wherever you have mentioned about the citations, for example, I said about an helicopter wherein okay, a food packet has been dropped from somewhere. Okay, so maybe you can mention, okay, so this has been useful in such kinds of studies. Okay, or where all the projectile motion, horizontal projectile motion, understanding this is useful. You can mention all this, right? Then statement about how consistent the data is with the scientific context. Finally, you need to mention this. So how good is your data? Is your data go hand in hand with the theoretical experimental values, and how consistent it is the experiment scientific context? Okay, what are all the scientific contexts which people have already done on it? Okay, and how does your experiment go hand in hand with this? Okay, so you can mention all this, and thus you conclude the experiment. Okay, I hope so. This is how, okay, a simple experiment like projectile motion can be handled effectively and considered to be completely novel, right? So with this, I come to an end to this particular video series for today. Tomorrow we will see some other experiment, and like my video, do really share and subscribe to my channel so that you get more updates regarding this. Shortly I'll be doing some other based on simulations and so on, so you will definitely get to know more about it. Thank you.